have conducted Mission Tenacity. They've met with a great deal of success. I want them to have an opportunity to share that with you. So, welcome.
Is there anybody that doesn't have slides that would like some? Yes. Dr. Martin. And then, yeah, there should be some sitting down there. Yeah, so it's slides, and then there's also a list of requirements there. Oh, sorry. D right there for you, and then number 7. So there's a list of requirements there as well, so you can reference them throughout the presentation. As I said, my name is Tom Fox, and I was the design team lead for the Atlas design team, and this is Mission Tenacity. Presenting with me today is Kyle Smith, my assistant design team lead, Destiny Jackson, Amatul Lazarine, Ahmed Al-Zayudi, Stephen Buck, Evan Valle, Nikki Syed, Julia Levitt, Colin Rogers, Jin Sung Lee, and Nick Steiner. A little bit of an overview of what we're going to be going over today. We're going to introduce the project, then we're going to go break through subsystem by subsystem. We have the structure subsystem, the securing subsystem, the electrical subsystem, the propulsion subsystem. Then we're going to look at how all the subsystems integrated together. We're going to go into the configuration management and finish it up with the conclusion. So here we go into the introduction. So what is our project? So we designed a demonstrator that was on air bearings to go and attach to an asteroid, as you can see over here. This is what the final CAD model of the demonstrator looked like here. So our fundamental objective was to develop a technology demonstrator that approaches a target body in a controlled manner and then attaches to the target body. So this right here is the demonstrator that we actually constructed. Right here was the securing mechanism, and then this right over here, this rock on this face, that was the asteroid we attached to. And then to test that we attached to it, we used this pulley system to put a 5-pound force normal to the target face. So a little bit of a concept of operation. So first, right here, we have the air bearing table, and then this would be the target. So the demonstrator would start off the table, make sure everything was good. We'd check to make sure the table was clean. There would be no dust on the table. There was no damage. Then we'd put the demonstrator on the table. We would power it up. We would connect the air bearing lines, and we'd do a systems check to make sure all systems were go. We would then start maneuvering over to the target itself by translating, and then rotating, and then translating, and then finally attaching to the target. Once we'd attached to the target and determined we were attached to the target by doing a stuck-on thruster test, we would then attach a 5-pound force through that pulley system to pull on the demonstrator in this direction here. After we were done, we would disconnect the demonstrator from the target body. We would remove it from the table. We would remove it from the table and pull all the airlines off and make sure it was now free and clear. And we'd make sure, again, that we did not damage the test facility. So now the subsystems are going to go into the configuration of the specific subsystem. They're going to talk about the requirements of their specific subsystem. And then they're going to go into their most important tests. So we won't be covering every single test for all the requirements. We did do that. If you want to know more about that, we have backup slides talking about that. And then finally, they're going to wrap it up with lessons learned. I'd now like to pass it off to Destiny Jackson to talk about the structure subsystem.
Thank you, Tom. My name is Destiny Jackson, and I'll be going over the overview and requirements for the structure subsystem. In an overview, the structure subsystem is defined as the subsystem that creates the frame of the demonstrator for the other subsystems to connect to. As you can see right here, each part that we created was meant for the other subsystems. And then this is what the frame of the subsystem looked like once we finished completing it. So what we did is we created a bottom piece T for the air bearings. We created a bottom weld that we welded together at 90-degree angles and a sheet for the securing and electrical subsystems to rest on. Then we created these corner bars for the top weld to sit on for the propulsion subsystem. Requirements: the structure subsystem shall securely interface mechanically with the other subsystems. The air bearing support arm shall deflect no more than 0.25 inches in the vertical direction, and this is to prevent damage to the testing facility. We shall be able to withstand all loads associated with demonstrator assembly, transport, testing, and operation without plastic deformation. The area shall be no smaller than 1 foot squared and no larger than 3 foot squared, and this is so that the demonstrator can move on the 6 foot by 4 foot testing bed with the ability to maneuver to to our target. We shall provide attachment points for the air bearings, shall weigh less than 50 pounds, and shall cost less than $300. Now I'm going to pass it on to Amadou Azreen, and he'll be going over the tests for the structure subsystem.
Thank you, Destiny. My name is Amadou Azreen, and I will discuss the tests that we did on the structure subsystem. Interface test. So the purpose of this test is to verify that the other subsystems components are securely attached to the frame. And the way we verify this is by hanging a 5-pound weights on the different parts, different locations on the components and other subsystems. Listed down here is the subsystems components that we tested and how they are attached to the frame. With the test that we got, there was no shifted parts detected, therefore the test passed. Next is the test facility compatibility test. The purpose of this is to verify that the air bearing arm does not deflect more than 0.25 inches in vertical direction. And the way we verify this is by placing a 1.5-inch height wooden block where the air bearing placed at right over here, here, and back there, and measure the height difference between the demonstrator base and the support points. In preliminary design, the analysis value that we got was 0.12 inches deflection. However, during the tests, we found the value deflection to be 0.22. Although the value is a little bit higher than the analysis value, it falls still under the value that's set by the requirements, which is 0.25 inches, before the test pass. The difference value that we got between analysis and test, we believe it is due to inaccurate measurement tools that we use. Next is the deformation test. The purpose of this is to verify that our demonstrator could withstand loads associated with its assembly, transport, testing, and integration and operations. One case that we consider is assuming a person lean on one side of the on the frame. Therefore, we verify this by hanging a weight on one side of the frame, as you can see here, the picture on the right. And then we add the weight slowly from 30 pounds up to 100 pounds. Again, in preliminary design, the analysis value that we got turns out to be 24,196 psi, which is still less than the yield strength of aluminum 6061, which what we use to create the frame. Therefore, there shouldn't be any plastic deformation. During the test, there was no plastic deformation detected, therefore the test passed. Now I shall pass it to Con Rogers to further discuss structure systems.
Thank you, Reen. I'm Colin Rogers. I'll be going over the structure subsystem. So the final test for the structure subsystem is our stability test. This was done to show that we met the manufacturer's recommendations of having our air bearings placed, creating an area larger than our planform area of our demonstrator. So we measured the distance between our air bearings and calculated the area in between. So the analysis value we got based on our CATIA design was 2.75 feet square, and the measured value for our area was also 2.75 feet square. And this was larger than our planform area of 2.48 feet square, so therefore our test passed. So to summarize all the tests we perform on our structure subsystem, we have this overview chart showing our requirements, description of each requirement, the analysis value compared to our test value, and whether or not the requirement was met or not. So as you can see here, all of our structured requirements were met and passed all the tests. So some of the key lessons learned by the structure team in creating this demonstrator was that designing parts to be machined is different than designing parts that work in CATIA. Accurate models make analysis easier and better, and precise measurement tools are important when doing tight tolerances. I will now be passing it off to Ahmed Al-Zayudi to go over our security subsystem.
Thank you, Colin. Hello, my name is Ahmed Al-Zayudi, and we're going over the security subsystem. Firstly, we define the securing subsystem as the subsystem that's responsible for securing the demonstrator and holding it to the target body. Here you can see a CAD rendering of an overview of the securing subsystem. Here is the picture of the fully assembled securing subsystem, which consists of a base and has two base supports, front and back. And the close consists of two outer arms, two inner arms, a track, and a gear that's connected to a servo. Here you can see an animation of how the securing subsystem works. Firstly, when the servo is turned on, it turns the gear, which pull both the outer arms and track back, and then the inner arms pivot around this point, thus executing the close and holding the demonstrator to the target body. Next, I'll be going over the requirements of the securing subsystem. The securing subsystem shall withstand a minimum force of 5 pounds applied normal to the target face. The securing subsystem shall secure within 5 attempts, shall consume no more than 5 watts of power, shall not damage the test facility, shall weigh a maximum of 20 pounds, shall cost a maximum of $300. Now I'll pass it on to Nick Said to continue talking about the securing subsystem.
Thank you, Ahmad. My name is Nikki Said, and I shall go over the test that we performed for our securing subsystem. So the first test that you see here is the 5-pound pulley test. This is to verify that our subsystem is capable of withstanding 5 pounds of force. And how we tested it is that the test was consisted of applying 5-pound force normal to the target body, that is via the pulley system here, which is located off the test bed. And this was done 30 seconds. And how we ensure that the test was properly done is that we visually inspect it and see that our demonstrator remains attached under these testing conditions. And next, we analyze this value. We were able to predict the gripping force, and it could withstand the 5-pound force of load. And then the test value that we tested which was 5.148 pounds, which is more than the 5-pound weight. And then we were able to remain attached for 30 seconds, therefore the test is passed. And next is the attempt test. As you can see here, this is to verify that the subsystem will secure within 60 seconds of entering the securing zone. And how we tested it is we divided it into 2 parts. The first part is to visually inspect that our securing subsystem is within the securing zone here, which is defined as 3 foot by 2.5 foot. And it starts the time as soon as it enters the securing zone, which has 60 seconds of each attempt. And to ensure that it's properly done, we perform a stuck-on thruster test to make sure that the demonstrator remains attached. Next, the analysis value, we come up to be 60 seconds. So how we did this is that we calculate the servo speed, and we got to know that it takes half a second to open and half a second to close. And therefore, in 60 seconds, we're able to do it in 60 times. And we believe that that's more than enough time to perform the attachment. And with the test that we performed, we proved it that we can do it under 60 seconds, which was 12 seconds, which was our best record. And it remained attached throughout the stuck-on thruster test. Therefore, the test is passed. And next, I shall pass it on to Kyle Smith to further discuss on our subsystem.
Thank you, Nikki. Hello, everyone. I'm Kyle Smith. I'll continue talking about the structured subsystem. So the next test that we did was the test facility compatibility test. And what this consisted of, or the purpose of this test, was to make sure that our subsystem did not damage the test facility, that being the air bearing table that we were on. So to make sure that we weren't going to damage it, we did a test in 3 parts. One, with testing our securing subsystem and how it attached to the target rocks off that air bearing table. And then after that test was passed, then we mounted the rocks to the board, the supporting board for the target over here. And then we tested again on the air bearing table, make sure we didn't pull the rocks off. And then the last step was to test it and check it during the 5-pound pulley test. So our analysis of this was to look at the bearing strength of the rock to make sure that our grip strength wasn't going to crush the rock and break stuff off. And we were under that. And with our test itself, we passed all 3 of those tests to make sure that we weren't going to break any rock off. And here's an overview of all the tests we conducted on our securing subsystem. As you can see, we have the requirements, the description, and analysis value compared to the test values. and we were able to meet all of our requirements for our security subsystem. So some of the most important lessons learned for our subsystem was knowing the difference with how a design is met in CATIA versus how you can actually assemble it in real life. It was a little bit of a challenge when it came time to actually build it for ourselves. So now I'll pass it on to Stephen Buck to talk about the electrical subsystem.
Thank you, Kyle. As you said, I'm Stephen Buck. I'm the electrical lead for the Tenacity system. So this is the CATIA model for our system with our LiDAR placed in the approximate position of where it should be on the final demonstrator. As you can kind of see underneath the power interface board, which doesn't have our components just due to complexity of actually modeling that, is our controller. And then our battery there is a 23-volt LiPo battery, which is not the same as one there due to some component failures that are not within our control. So this is the actual physical picture showing the approximate positions, once again, of the LiDAR, and then of our power interface and controller, which you kind of hard to see there, and then our battery placed inside of its cage in its approximate position on our demonstrator. This is the graphical user interface that our operator was using to actually control all the functions of our demonstrator. All of the sensor information, so for the LiDAR, angle, velocities, and Y position are all just simulated just simply for the picture, as just when I took the picture, there was no sensor connected. For actual operation, it is either with keyboard shortcuts or just simply pressing the appropriate buttons on the screen now in the GUI to actually control each separate set of motion. The stable there allows it to actually stabilize into a single set position of when that button is pressed. So our requirements, beginning from our main one is that we have to be able to provide power for at least 15 minutes to the demonstrator. Our controller has to have a latency of less than 3 seconds. Our controller needs to be able to provide the state vector of the demonstrator to our operator. The entire subsystem has to weigh less than 10 pounds, and the entire subsystem has to cost less than $350. These requirements are for our sensors, for our sensor selection. First, we have to be able to determine our velocity within plus or minus 1 feet per second, determine our distance to our target within plus or minus a foot, determine our angular velocity within plus or minus 6 degrees per second, and determine our angle to the target within plus or minus 6 degrees. The first test that we ran was our power test. Inside of that, we actually ran 2 separate tests for it. The first was worst case scenario, so this was running both our securing subsystem controller and 2 solenoids continuously for 15 minutes, just ensuring that everything was running that entire time. The second test we ran was normal operation, so actually having it on the table and just controlling it around until we felt pretty good, which was after about an hour, and even then there was still quite a bit of charge left on the battery. So when we did our first analysis on our power test, we estimated about 1.57 hours. That's just running off of the data sheets that we were seeing for power consumption for all the components and just what the energy on the battery had. Our actual test values was 2.05 hours, and that was actually taken from measuring the current of each of the components, as our solenoids actually drew less current than what the data sheets specified on them. I'll now hand it over to Envai to go over the sensor tests and the rest of the subsystem.
Thank you, Stephen. I'm Evan Bai, and I will continue discussing the electrical subsystem. So first, I'm going to talk about the velocity and distance tests. So in order to perform these tests, we set up this test rig right here, which essentially what we'll do on the front, we'll mount the LiDAR, we'll have the controller to control the sensors. There is a breadboard here, which will have the voltage regulator, the IMU, and also do some signal routing. And then we just had a temporary power supply just made of AA batteries in series. This test was to verify the requirements of the distance should be determined in plus or minus 1 foot, and the velocity needs to be determined within plus or minus 1 foot per second. And then for the angular velocity, angular rotation test, we used essentially the same test rig for the previous test, and we put it on this 3-axis rate table. And what this rate table do, what we used it for is this black disc right here would spin, and that would be able to simulate an angular rate and an angular rotation to verify those tests. And this was to find that the angular error for position was within plus or minus 6 degrees, and the angular velocity was in plus or minus 6 degrees per second. And so this is the results for those 4 tests I just mentioned. As you can see here, we passed all of them. In this here, we have the analysis values for all of these. These analysis values were taken from data sheets for these sensors. The ones to note here are the ones for the IMU, essentially, the angular ones. The IMU data sheet read that it could, its accuracy was in 35 milldegrees, which was not very correct as we were able to determine. And so the discrepancy here is due to the inaccuracies within the data sheet. And so this is just a summary for the analysis for the tests of all of our testing requirements. As you can see here, we passed all of our requirements. The major one to note is that for our analysis for budget and for weight, we were a little overweight and a bit over budget. We were still within the requirement. Also, our controller basically had instant command to response time, so there was no measurable latency. And as we already discussed, we were able to pass all of our sensor requirements. And so for some lessons learned, the big one is, I'd say here is time management and the change in concept of operations due to a change in test bed. If we were able to change this, we probably would have purchased a different component, such as a more powerful IMU over the LiDAR. And I'll now pass off to Nick Steiner to discuss the propulsion subsystem.
Thank you, Evan. So, we were faced with the problem of propelling our demonstrator across our air-bearing table, and we approached it in the following way. We decided to come up with a cold gas thruster system. We decided that cold gas was our best option because we didn't want to damage the test facility. Any other sort of monopropellant thruster would have been not ideal for our facilities. So we came up with what you see above, a CAD drawing of our final design. We have an air distribution manifold at the top, which takes shop air, so a wall supply air via nylon tube into the top and distributes it to the solenoid valves, there are 8 of which, 1 per thrusting pair, and those are then plumbed into a nozzle for a thrusting pair. There are 4 thrusting pairs on the demonstrator, so we turn on 2 thrusters at a time. This is our fully realized design. As you can see, everything is laid out as it is in the CAD, and yeah, that's just the way it is. So, we're going to get right from there into the requirement. How did we decide whether or not our cold gas thrust system was working? So we decided that we needed 0.2 pounds of thrust. That is a total thrust generated by 2 thrusters. The total mass of propellant consumed by the propulsion subsystem shall not exceed 1.5 pounds mass. The propulsion subsystem shall operate using a maximum of 24 watts. The propulsion subsystem shall not damage the test facility, shall weigh a maximum of 30 pounds, and cost a maximum of $350. That takes us right into our tests. The first test we performed was a pressure loss test to verify the pressure in the chamber of our nozzle. We needed to do this in order to make sure that we turned our regulator pressure up to the design point that we designed our nozzles to. So, we found that we had, we needed 70 psi in the chamber, and we got the pressure loss between the reading from the inline pressure gauge, which you can see on the right, and the regulator at the wall. So our analysis value was 2.91 psi, and we found out through testing that our actual value was 40 psi of loss. We believe this is due to improper frictional coefficients of the tubing. We didn't have a spec sheet, and we estimated them using a Moody diagram. However, we still passed our test. We analyzed that we could not have more than 50 psi of loss, and we had 40 psi. So now I'd like to hand it off to Julia Levitt to talk a little bit more about the tests that we've done on the propulsion subsystem.
All right, thank you, Nick. My name is Julia Levitt, and I will continue to discuss the propulsion subsystem. So the next test that we would like to highlight is our minimum thrust test. The purpose of this test was to verify that the total thrust produced by the propulsion subsystem exceeded or was equal to 0.2 pounds. So the way we performed this test was by building a thrust stand, which is shown in this image. We then attached one thruster, which is the nozzle and solenoid valve, to the stand and set it on a scale in order to measure the thrust produced by a single nozzle. We then multiplied this by 2 to get the total thrust. So again, our analysis value was 0.20 pounds, which is the same as our requirement value, which was derived based on the number of maneuvers, expected maneuvers that can be completed over 300 seconds. Our test value of 0.16 pounds was less than our requirement value, so we did fail this test. One of the reasons we think our nozzles may not have performed as designed was due to boundary layer effects at the throat of the nozzle due to the extremely small throat size of the nozzles. In addition, it's important to highlight that our requirement value of 0.2 pounds was based on the demonstrator weighing roughly 80 pounds, and in actuality, it weighed about 19 pounds. So even though we did not meet our thrust requirement, we were still able to perform our mission successfully. The next test is the propellant throughput test. The purpose of this test was to verify that the total propellant consumed during the mission did not exceed 1.5 pounds. And to perform this test, we placed a rotometer, which is shown in the photo here, in line with a thrusting pair, similar to the setup that Nick discussed in our pressure loss test. We then measured the volumetric flow rate using the rotometer, converted that to a mass flow rate, and extrapolated over 300 seconds to calculate the propellant consumed over 300 seconds. So our analysis value for this test was 0.67 pounds, and our test value was just over 1 pound, which is less than our requirement of 1.5 pounds, so we did pass this test. And just over 1 pound of propellant was based on the measured flow rate of 27 standard cubic feet per hour. So to summarize, all of the propulsion subsystem requirements were met with the exception of our thrust requirement, which we did not meet. But once again, we were still able to perform the mission successfully with the thrust that we were able to produce. So echoing what some of the other subsystems mentioned, knowledge of the machining process would have expedited the design process of our nozzles. In addition, throughout this project, we were able to see how assumptions made during the design process don't always translate to the physical world, which shows the purpose of the building and testing process and the value in that. So now I will pass it on to Tom Fox to discuss system integration.
Thank you, Julia. All right, now we're going to go over the system integration and the system integration piece. So once again, here's the demonstrator, and I'd like to highlight that right here, this top line, that's where the air is supplied for the propulsion system. You can't quite see it, but there's a block under here, I'll point it out on the actual demonstrator, that also has an inlet valve. That is so that we have air supply for the actual air barriers. Both of those come out of the wall in the robotics lab. Just to clarify how that works. So here's the actual demonstrator floating on the air bearing table coming into the target here. As you can see, it floats almost frictionlessly, and here's the air lines coming in from the ceiling and from the wall of the robotics lab here. There is a little bit of a disturbance force caused by these air lines, but not enough to cause us any issues in this project. So going over the system level requirements. So we wanted our system to be able to translate at least 3 feet, starting under its own power from a starting point. We wanted to be able to rotate 90 degrees under our own power. We wanted to be accurate within plus or minus 1 foot. We wanted to be able to complete the entirety of mission Tenacity within 10 minutes. We wanted to be able to survive 2 stuck-on thruster tests, one which creates disturbance force and one which creates disturbance torque. We wanted to be able to withstand a 5-pound force applied for a duration of 30 seconds, normal to the target face, once the system is deemed to be secured to the target body. We wanted the center of mass to be within a 2-inch by 2-inch area around the geometric center of the base. We wanted the system to weigh a minimum of 60 pounds. We wanted the system to weigh a maximum of 150 pounds. We wanted to interface safely with the test facility. We wanted to cost the Atlas design team a maximum of $1,563. We wanted to be completed by December 7th, 2018 today. All right, first I'm going to go into the translational ability test. So this was to verify the system can translate 3 feet under its own power. So we basically had the system start at rest behind this block here. Between these 2 arms, that's 2 feet. So it would be right about to here was the 3 feet under our own power. We tested this in 4 different headings. So facing this direction, having the demonstrator rotated 90 degrees and translating again this direction sideways, backwards, and then once again all the way around at 270 degrees. So when we did our analysis value, we based it that it would take about 14 seconds to translate, with it weighing 60 pounds and there being 0.2 pounds of thrust. But in our actuality, it took us about 5.26 seconds on average to translate. Here you can see the times based on the different headings. The reason the times are slightly different are because as we translate, our center of mass was not exactly dead center, so we rotated a little bit when we were translating in certain headings here. So again, some of the discrepancies here are 60 pounds versus 20 pounds, and the thrust levels were slightly different, but we did pass the test as we were able to translate that 3 feet. Next, we're going to talk about rotating. So this is the same thing. We wanted to rotate at least 90 degrees. So that's to be able to adjust our which direction we were facing. So we set the demonstrator in the center of the table. We fired 2 thrusters opposite each other. So we fired this thruster right here and this thruster right here. And that would push us around in this direction. But we tested in both directions. When we analyzed this, we said that it was going to take us about 23 seconds to rotate, but in actuality, it was right on average about 4.1 seconds. Slightly different in both directions. Once again, it's the same discrepancies that the weight was slightly different and the thrust was slightly different. So then we tested the accuracy of the system. We wanted to be accurate for a demonstrator attachment point, which we said this reference point was the dead center in the securing claw here. Wanted to be able within plus or minus 1 foot of a target location here. Going through this, we didn't really have a way to analyze this, but during testing, we were actually within 3 inches, which was very successful. A little bit of the discrepancies was there's a little bit of airline interference, so as you got closer to the targets, the airlines would pull you slightly to the left, and our thrust vector was not quite through our center of mass. Next, we wanted to verify that we could complete the entirety of mission tenacity within 10 minutes. So we wanted to have the demonstrator start at this end of the table, facing this direction, and then maneuver over to the target like so. So I'd be translating the 4 feet, rotating the 90 degrees, and then attaching to the target. So we thought this was going to take 10 minutes. We analyzed that this was going to take 5 minutes based on our propulsion system and our securing subsystem. It actually took 30 seconds, and then after this, having fun testing the demonstrator, I think our best time was about 18 seconds. So we were much more accurate than we expected. There was a lot less airline interference than we were kind of initially expecting for. Finally, a stuck-on thruster test. So once we attached to the target itself, we wanted to see if we were attached. So to deem ourselves attached, we would say that we're attached, we visually confirm, and then we perform 2 stuck-on thruster tests. The first would be to create a disturbance force by firing this thruster right here and this thruster right here. So they would put a thrust vector in this direction right here and push the demonstrator like so. And we hold that for 10 seconds. After we pass that stuck-on thruster tester, then we would fire this thruster right here and this thruster right here to create a rotational force like this and put a torque on our securing mechanism. And we would once again hold those thrusters open for 10 seconds. So we analyzed that we were going to stay secure based on how much gripping force we had, and in our test we did stay secure. And once again, the thrust was slightly different. Center of mass attack. So we wanted to verify the system center of mass was within a 2-inch by 2-inch square within the geometric center of the demonstrator. This was so that when we fired the thruster here and the thruster here, the thrust vector would go almost through the center of mass with a little bit wiggle room right there. And then we checked the height of each corner to make sure, and we checked to see if it would fall off it. So here it's facing from the front. You can see that it's slightly, let's see right here, you can see that it's slightly tilted forward, but it still stayed balanced, and we did pass this test, so there's no discrepancies of note. Finally, we wanted to do a weight test. We wanted to verify the system weighed between 60 pounds and 150 pounds. These weights come from the air bearing, new way air bearings, and they're recommended heights that you wanted to sit off the table. So when we first contacted New Way air bearings last year, they said that the optimal range for the air bearings to sit off the table was 5 microns. Now when we were running 3 40mm air bearings, that would mean we wanted a weight of about 60 pounds to about 150 pounds. So that's where those numbers came from. When we actually called them this fall, they slightly changed their story when we talked to a product manager and said that what happened when your weight was lighter was that you could have some bouncing effects, but based on our tests and what we were doing with our project, the bouncing effects did not affect our projects, so we didn't need to add the ballast weight to move ourselves up to this 60-pound number. So we did fail this test because we were not at 60 pounds. But that again comes from the ballast weight. We did have 40 pounds of allowable ballast. We could have gotten ourselves up to 59 pounds, which still wouldn't have been 60. But we decided that was working against ourselves, as it would hurt our cold gas propulsion system, it would hurt the other performance, and it wouldn't actually help the air bearings for our project. Next, we wanted to make sure that we didn't damage the test facility. So we verified this by inspecting the test facility. We added bumpers around the side here, and we just wanted to make sure everything went okay so that the testing facility was in the exact same condition that we found it in. So we used an inert gas in our cold gas propulsion system. We made sure all the parts were secure. We filed down any sharp edges. We put those blue bumpers around the edge of the table so that the demonstrator couldn't fall off the table. And we made sure that we used no projectiles in our securing system. And yes, no damage was observed, so we passed this test. Finally, we wanted to verify that we cost less than $1,563. So this is all costs, including tax and shipping. So our total cost was $813 after all the subsystems. We came in well under budget, which was we were very happy about. Our biggest cost was the electrical subsystem. This was partially due to having to reorder parts after some of the parts failed on us. But otherwise, we did very well. Some of the slight discrepancies in analysis was tax and shipping was not always incorporated in our initial analysis values and those broken parts in the electrical subsystem. So going over all of the things, we passed all of our tests on this page. So we were able to translate 3 feet, rotate 90 degrees. We were accurate within a foot. We took less than 10 minutes. We passed our stuck-on thruster test. We were able to withstand our disturbance force of 5 pounds for 30 seconds. Our center of mass was in the geometric center of a 2-inch by 2-inch square. The only test we failed was the 60-pound test, and once again, I went over that earlier. But we were under 150 pounds. We did not damage the test facility. We did cost less than $1,563, and we are completed before today. Now I'd like to pass it off to Jin Sung Lee for configuration management.
Thank you, Tom. Hi, my name is Gina. I'll be going over the configuration management of our system. And I'd like to quickly go over the 17 different configurations that we had, starting from the start of the preliminary design to the end of the detailed design phase. So the first configuration you're seeing up here is the first ever configuration that I put all together after doing the trace study of all the parts that we felt was required to have a successful mission. And when this came together, we did a lot more research into how everything had to be placed in order to have a successful system. And as we did more research, we came to a configuration 6 where it had two 6-inch extra spacer in the front of the air for the 2 front air bearings and an 8-inch spacer in the back air bearing to create a perfect equilateral triangle to have a stable configuration. And also, instead of having 2 tanks from configuration 1, we decided to go to use a tank that was big enough to provide a requirement that we had prior to detailed design, which was providing to us for 10 minutes with its own tank. And the next configuration 9, which was the configuration that we used to present our preliminary design reports. And after this, we had a very long summer. When we came back, we completely changed our propulsion subsystem. We decided to no longer use the tank, but rather use the shop air from the Space Robotics Lab. And during this time, we got the donations from Colin's parents. Those rocks over there, which was the rocks that we made targets out of. And we figured out that the mechanism that we had for the securing subsystem at the time was not going to work so well with the target that we made. Therefore, we have completely revamped our securing subsystem to have contracting arms and a retracting track to hold on to the target. And to be able to give enough clearance at the back of the securing subsystem's track to track back, we had to create this electrical component mount, which had enough space in the bottom for the track to track back. And when this configuration was completed, we had a meeting with the workers in the XFAB and figured out that there's a lot better way of putting everything together. As you can see in the next. Instead of bolting all of the parts from the top and the bottom or the entire demonstrator together, instead of doing that, we cut a lot of the parts in 45 degrees and welded them together. We welded the parts that didn't have to come apart after we completed the demonstrator's build. Therefore, we welded the top, bottom, and the bottom L bar completely to itself. So so that way minimizing the amount of bolts that we had to use. And also during the testing, we had noticed, not during the testing, before we tested, we noticed that the LiDAR was very close to the target. Therefore, we gave a spacer to move the LiDAR a little bit backwards to not damage the LiDAR during the testing. And that is the final configuration that we worked off with, and that's what we have over there. Next is the product structure tree. There's two main trees here. We have the demonstrator and the test facility. As you saw before, we have a 4 subsystem under the demonstrator and all the parts that we needed to run the demonstrator under the test facility's structure tree. The documents are under process of being released. All the bill of materials, part number is hyperlinked to their distinct draftings. So if you click on any of these numbers that is hyperlinked, it will take you directly to that part's drafting, so you'll be able to find the draftings very easily. Thank you. Now I'll hand off the mic to Tom Fox to conclude our presentation.
Thank you, Jim. Going into conclusion. So first, we're going to go over some of the major milestones of the semester. On September 19th, we had our critical design review. That's where we looked at it for the first time, and we went into the building phase right after that with our critical design document and test plans. So right after this, we started fabrication. While we were doing the critical design document and writing the test plans, we were starting to build the actual demonstrator itself. On November 2nd, we had our conformity inspection, where when he showed you that bill of materials and those drawings, we confirmed that what the designs were is what we actually built. And today we have our final system verification review. Some of the main lessons learned just on an overall project are delegation. That was a huge one, especially for me as the design team lead. It's having other people help me out with stuff and doing the whole thing. Time management was also crazy. We did a lot of work with submitting documents this semester and actually getting the documents, rough drafts submitted early so we could edit them and turn in an overall better project. Communication was huge. For example, when the securing subsystem was adjusted, we had to build this box for the electrical subsystem. When that first happened, there wasn't a lot of communications between those subsystems, so we really had to work on making sure that all the subsystems could fit together in a fully integrated project. And then Professor Mangum really helped us with our technical writing and our technical presentation skills this year. And then everybody in the machine shop really helped us with manufacturing and figuring out how to actually work with real life materials and not just looking at CAD drawings in this class. Just some brief acknowledgements. First and foremost, we'd like to acknowledge Dr. White and Professor Mangum as our two professors for this class. They were so instrumental in designing this and building this, and just in the whole process of getting this all submitted and getting to this system verification review. We'd also like to thank Dr. Yale for being our preliminary design professor last year and getting us started on this project and getting ready. And then Dr. Benavides for being here today and who's at a lot of our other presentations and giving us a lot of feedback along the way, as well as Dr. Fabian, Dr. Eisenberg, and Dr. Schulz. Then we'd like to thank Jeff Hyatt, Patrick David, Jared Vanetta in the machine shop for helping us weld the parts and helping us actually build the demonstrator itself and get it fully fabricated. And then Jim Weber and Leonard Windholm for helping us order the parts and make sure everything got here on time so we had parts to build the demonstrator. Then we'd like to thank Mrs. Rogers for donating the target surface that we used. And then finally Tristan Minkoff for sitting in for some of our practice presentations and giving us some feedback. Quickly going into the programmatics of the semester, totally as a team, this semester we spent about 1960 hours, total hours. Most of that was in engineering, as you can see up here, and that broke down to an average of 11.66 hours per member. Now if you look up here on this graph, this line was the kind of expected going into the project at 14 hours a week, and as I said, we're slightly below that 11.66. I partially attribute that to being so successful right at the very end of the semester, where it dropped off when everything started to work and we didn't have many problems with a few of the subsystems, so people didn't have to be constantly working and getting it right, because once it was right, it was right. Next, I'd like to show a short video of us actually in action and invite my team up, because we're going to get ready to answer some questions. Right here, this is kind of the initial drawing phase in CATIA and getting it all built. Some of the initial configurations and how they looked with the old tank. And then that was our first mock-up in our presentations last semester and what we thought it would work. That was our second mock-up after we had a different securing system in the tank. Then we changed it this semester to have the claws and our final kind of CAD rendering. And then we were water jetting it all out for the securing mechanism there, welding the top piece in this picture, getting it all assembled together and built. Ask you all to join me up here. Open up the floor to questions here. I think there's some microphones. I have no idea if they work. If you like them, turn them on. Hello? It's green, I think. No, it's yellow. Colorblind person microphone, that's all.
Test.
Perfect, got a microphone for you if you want to start out.
All right. So first off, I guess I'll start by saying that was very impressive. That was a very good presentation. It was a very good project. It was incredibly thorough. There was a lot of information, almost to the point of being too much. And I think you guys did a really good job going through it. The only thing I think you guys missed out on is all the fun of problem solving. When something goes wrong, you got to fix it then and there. And it looks like you guys did have some of it. But, it's very impressive that if you guys built something that complex and you had no major problems. That doesn't happen very often. So good job, you guys. So first question, just to top level, because I was a little confused about this at the beginning. What is the end goal of this project? Like, what was the inspiration? Is this like you're just trying to latch onto something, like the docking? Is this like mining, robotic arm?
So the inspiration behind this project actually came in one of my previous classes in the space systems classes when we were trying to meet up with an asteroid and doing that. And then we realized that we couldn't actually attach to this asteroid because it was about 1 kilometer in diameter, didn't have the gravitational parameter for us to dig into the asteroid. So we're working on the actual problem so that we can secure the asteroid and then use some sort of scientific equipment to dig into the rock and look at maybe asteroid mining or try to figure out like signs of solar system formation or maybe even look for RNA in the ice of some asteroid. So we want to be able to attach to the asteroid and then study it.
Okay, fair enough. Yeah, because with what the project is, you guys have a lot of applications in the astro field, so it was didn't want to project what I was thinking on it because I have a very specific view on that. Okay, where to start? I mean, you guys had lessons learned, so that helped with a lot of things. Let's start with slide 105. We'll move backwards. So, there's one up here that made me laugh, and that was manufacturing. Well, sorry, delegation made me laugh too, but manufacturing. So, had any of you guys had any like machining experience? Any the rest of you guys? Just you? Metal, wood, all the above?
Metal,
ceramics?
wood, all the above. I was a mechanic for 8 years.
So that was the problem, that you had one person who had experience, and, okay, okay, I understand that. I asked because on my team, we had a lot of people with experience, so it was interesting. You don't normally see manufacturing as a lesson to learn per se. Can I inquire as to what the specific issues that you guys ran into were?
One of the specific issues was if you like look at the, like first we had everything assembled with nuts and bolts and nothing was welded. And then when we initially had this front piece welded, only the front was welded here, so this piece actually cracked when this moved up and down. So it's stuff like that that kind of came along. But there was a little bit of tolerances when we were trying to figure out how stuff fit together.
That's a big thing I was wondering about was tolerance stack, because you got a lot of pieces just fitting together. Okay, slide 107. So, that's a big gap between actual. Now it's in the right direction, that's a good thing. You're still going to get asked why there's a big gap. So you said that nothing really went wrong, nothing really, you didn't have any major problems. So the next question that comes to my mind then is, how could you have planned better from the beginning, knowing what you know now, not to get that gap closer, but to make sure those problems that I know didn't happen in this case wouldn't have happened? Does that question make sense?
Can you restate it, please?
So what I'm asking is, how do you plan to avoid problems that you guys managed to avoid? You seem to be aware that you avoided a lot of problems. So what did you guys do right is what I'm asking?
We did a lot of like system engineering. Jin really helped with the configuration, making sure that everything was actually going to fit together before we started assembling stuff. So there's a lot of really good CAD drawings out there that we had that weren't just like, we think we're going to do this. We had a really good set plan in stone, and we had a lot of people from a lot of different disciplines on this team, which really helped in getting everything assembled. Like, I'm not very good at electronics, and Steven and Evan are both really, really good at that. And so they really helped us in that aspect of it, to where I would have had no idea. So it really helped that we had a diverse team that could all plan for our different things and our different areas of expertise.
Okay.
I would say another part tagging on is the budget, because I helped handle our budget. We made sure to plan for the event that we'd have to buy something twice. So for electrical on their side of things, that resort to that, but for everyone else, we didn't really have to worry about that, and that's why our budgets for all of our subsystems were way under, because we tried to account for any mishaps down the road.
And again, don't take this as a telling you did the wrong thing. It's just when something goes this well, it's very important to step back and say, why did it go this way? Because that is something that you want to transmit to other teams. You want to explain, be able to communicate to them, this is what happened, this is what worked well, this is why the success happened. It's the failure analysis in the reverse. So I would highly recommend, you guys have probably already done that, but if you have not, please do so for the benefit of teams following you.
And Dr. White was also instrumental in helping this project. He gave a lot of foresight of, there's going to be an issue there, as well as the machinists when they came in and looked at our design. And you might want to think about this. So it also really helped to be surrounded by very great faculty.
Good to hear. I guess I'll be talking to you soon after this. Slide 1 more, please. This was really good. I was glad that you guys were showing it in this format because it was very quick for me to tell, here's what you analyzed, here's what you tested, requirement was met, and it had the requirement on it. Very quick, very easy, very good. Another question. Slide 71, please. So, knowledge of machine process and effects of assumptions made during the design process. And I'm referring specifically to the nozzle in this case. Did you guys have any empirical data on nozzle performance?
The only data that we really had on nozzle performance was thrust, but when we went through and we were designing, we were doing all of our analytical stuff, we had looked at everything, including like pressure to exit, a lot of those things. The main one that we ran into, boundary effects, we didn't go into any further research with that. It wasn't something that we were expecting, and it wasn't something that we went back and analyzed after the fact.
Okay. that might be something worth doing if you guys have the time. But obviously, probably a little more focused on other things right now. Yeah, because that was, to me, a little strange that you have those concerns because it's a, normally they issue it with the empirical data, normally that's enough. But again, I don't know the specifics of it, so I'll leave it alone. Actually on the same slide, what did you guys not know about the machining process for these nozzles that you wish you had known?
There's a few things that we had just that were just short-sighted. We were kind of just knowing enough to get us into trouble. When we were designing them, we wanted to make them out of round stock. So round stock will chuck up real nice and easy in the lathe and in the mill. It'll work really easy for the machinists. And it was kind of a square peg, round hole kind of thing where we ended up having to put these circular nozzles on top of the demonstrator when we did our review with all the people in the machining shop. They came in and said, well, why don't you just make it flat and bolt it down? And I'm like, whoa, yeah, that does sound, when you say it like that, it sounds obvious, but just things that, maybe we couldn't see past, we had our heads a little too low when we looked at the picture. Couldn't step back and see those things.
Okay, so maybe coordinate with the machinists a little more next time, which admittedly the guys here, they see a lot of strange things, so they have a lot of good ideas. Very good. All right, well, in the interest of time, I'll stop there. Great job, you guys.
Thank you. Thank you.
So it sounded like you guys expected this to weigh a lot more based on what your supplier for your, what do you call those, little air hockey things?
Yeah,
told you, and knowing now that you could make this a whole lot lighter, what would your next improvements be? Because you guys just use your apps to every single requirement you pretty much set out to do, so. Where was the challenge? What do you want to do next?
What do we want to do next? I think the next thing that if it was just me is I'd want to get that center of mass even more central in the demonstrator, because right now it's within that 2" by 2" square, but it's about an inch forward of the geometric center and then dead center side to side. If I had more time, I'd like to put more ballast mass on it to make sure that I could get it absolutely dead center so that all the thrust vectors would go straight through the center of mass, and it would be a little bit easier to control and there'd be a little bit less drift.
I know in terms of, I worked on the security subsystem, and because we only had time in the semester to work with one target, one of our tertiary goals was to attach to a variety of surfaces. So if we would have known that we could have, made it bigger or a different system to be able to attach to multiple surfaces, if we would have had the weight to be able to add more claws or potentially something else, if we knew we had more wiggle room to design bigger stuff.
Yeah. Because you were like 40 pounds underweight or something, right?
Yeah. Yes.
Yeah, you guys can do a lot with all that. There's a lot of room to play around. So what did you guys manufacture all this yourselves, or did the machine shop pretty much do it all? Or?
It was a combination of both. The machinist did a lot of the welding and then some of the drilling of the holes to screw it all together. We ourselves built both the wooden target, the pulley system, and put the rocks on the face there. So that was all student done, and specifically me. And then the electronics was mostly done just by the electrical people. And they designed the PCB board and then had it sent out and then come back, but it was their designed PCB board.
That's awesome. Cool. Great job, guys.
All right, guys. Good job. I'm pretty impressed with this, so well done. I want to talk first to the claw. Slide 28 and 29. So, did you guys take into consideration what the size of your target, and what you're limited to based on how big this claw is and its range of grabbing?
Yeah, we understood that we had a range of targets within that gripping size of our mechanism, and we knew roughly what the target size would be, that it would be within that range. We didn't quite know exactly what it was going to look like when we designed our system, but we knew it was going to be within a range, and that's what we designed our claws to fit.
And that was based off what, speculation of what a rock could look like or something?
Yeah, and the theory behind that was we would want somewhat of a target zone that we would aim for if this were to be an actual mission,
right.
And we would design our system to work under that target zone conditions. So for us, that was a target around this size.
Okay. The only thing is, unless I missed it, I didn't see a requirement for that, so it might have just been.
There's no requirement.
No requirement, is there a reason for that?
That was a little bit purposefully, because when we first envisioned this project, we didn't even know what we were gonna do as the target. The target was all designed this semester. It wasn't even considered really a preliminary design. It was just, we're gonna have a target.
Right.
So that kind of came forth in this design and seeing exactly what we wanted. And what was available to us with our budget and what we had.
I know a lot of the requirements are driven based on what you can do.
Yeah, exactly.
So, yeah.
And actually putting something on the air bearing table, we couldn't have anything set directly on the air bearing table, which is why this art contraption looks like it is. It slides over the glass so you can go and grab it. So that was the other thing, is something that we can actually support in the air above it.
Okay. Good. The rack and pinion gear, that's impressive. Is that manufactured?
Yes, we built the rack out of a half-inch by 3/4 inch aluminum bar, and then we cut the gear out of a piece of sheet metal on a water jet.
Oh, that's one of the water jets.
Yes, and that's what most of our system was cut out of, one sheet, and we welded all the pieces together.
Cool. So I'll move forward here, I think. I had slide 46 in my notes.
46.
46, yeah. So I can kind of talk a little bit here with regards to electrical and controller and things like that. I like the GUI, it's impressive. So was this, your controller, was this autonomous? Did you have a set of programs that you built and then executed, or was this manual, or how did that work?
The initial is that it's all manual. It's all manual, at least at the moment. We did have a secondary to try to make it autonomous. Unfortunately, I did not have the time, and additionally, our LiDAR actually, over a weekend of no one touching it, just destroyed itself, so it doesn't have any impact. So it only has the IMU information, so the only autonomous aspect of it that I can actually implement is just stabilizing it, so it's just stays facing a single direction.
So there was some controlling this while it was operating?
Mm-hmm.
Okay.
Yeah, and it's just through a laptop.
Cool.
Just
And
a
then,
Python program.
oh, okay. We're using some sort of RF versus wired?
Wireless. So it just uses, so the controller is a Beagle block wireless, and then we just connect to that, connect to it wirelessly, and then just connect to it, doing an IP connect to it in Python.
That's cool. So the last few things on the electrical, you had battery issues, you said?
Yeah, so we actually, the first time we had to redo our board, the 5-volt regulator destroyed itself and the traces around it. So we had to completely use the second of the 3 boards we got from Launch Park.
Oh, wow.
And that was part of why we had to reorder, is that kind of how we did it is it was kind of hard to remove the working components. And then the second time we put it on, the 12-volt regulator died. So we had to go from a 23-volt LiPo down to a 12-volt LiPo just to run everything.
Okay.
And I just have a jumper wire basically that just runs the solenoids from that.
Cool. Last question I had was, I like the cool gas thrusters. Where'd you guys get those?
Well, we designed them here and had the machine
But the,
on campus.
so those little solenoid, or, I'm not sure what those little black.
Oh, the solenoid valve itself?
Yeah, this is the solenoid, and this would be the nozzle.
So
itself.
it just opens and flow?
Yeah.
How does that work?
It's open closed.
Yeah, so they're normally closed solenoid valves, and when they receive a signal, they open.
Alright, well done. That's all.
Well, I was mightily relieved to hear at the end that you actually did have some problems with things destroying themselves, which is always nice to be able to blame the things rather than oneself. Like the other said, I mean, this is a very, very impressive project. Not just the presentation, and the video was very useful at the end. Not just fun to watch, but it was very, very useful. But you guys have achieved an astonishing amount of stuff in the time you've had, you know, to have built that, tested it, designed the whole system, in fact, and tested it. So well done on that. A couple of things though. My first question was a non-engineering one. You had a budget of $1,563. That's a very odd amount. Where did that come from?
So that comes from the Department of Engineering. It gave us about $1,500 based on the size of our team. And then there's $63 left over from Dr. Yale's previous detail semester. That was a donation. So we were given, it was $62.86 is what it was. So that money was just kind of given to us as a pass down.
So you're way under that, so I hope you donated it back.
Yeah, we will.
Okay. I mean, the long-term scenario for a program like this is to do the real thing. Now, you couldn't test the real thing because, you know, A, we're not on an asteroid, and B, we've got a scenario for gravity. So using an air bearing, which is absolutely fine. But a couple of things on that. In the little video you showed, the approach was fairly slow, at least it looked fairly slow, but you say you're measuring, on one of the sides it says you're measuring to 1 foot per second, the actual velocity, which infers that the velocity itself should be much higher, it was likely to be much higher than that, is that right?
So the clips that I used in the video, some of those weren't of our best runs through. Those were of like some just initial testing runs that I would happen to be filming that I used for our clips. And with that, it wasn't the best pilot that we had driving the system. That's why some of them, it was moving around and it didn't immediately attach. But our best run was about 30 seconds.
Okay.
I got more on your point here. Is when we initially had this table, it was a 10-foot by 14-foot table instead of a 6-foot by 8-foot table. So that was when we got those velocity sensors that we wanted within plus or minus 1 foot, because you had a lot longer distance to accelerate and a lot longer distance to decelerate, to where that 1 foot per second was would be more precise, as we weren't only moving a foot per second.
That's fine. That's an answer to from both of you. What was the real speed that you were hitting the end stop at? Do you remember?
Unfortunately, all the tests when it was actually on the table was after the LiDAR broke. And that was our most accurate sensor, the IMU. Unfortunately, by the time it actually got to the target, drifted quite a bit that it was kind of hard to.
Okay.
Really
And how were you slowing down, or was the speed of contact your maximum speed?
It was slowing down.
How?
Pretty much just pushing reverse. So it was just approaching forward at a speed, and then as it got to a certain point, the operator would just push reverse to slow it down.
Reversing using the thruster? Or
Yeah, we use the front two thrusters.
Okay, okay. Because here's the real problem that you've got, in the real world, which is that you would come in at quite a high speed, and you know what's going to happen. Well, first of all, you're not going to find a target like that to catch on to.
Yeah.
Very unlikely anyway. That's a little green man on the surface. But the next thing that will happen is that you'll bounce. And then having bounced, you'll keep going. Okay, you won't conveniently have somebody there punch you back. Because if you think back to the Rosetta mission, which landed, albeit on a comet, not an asteroid, but it was a big comet, had the same problem. And it didn't bounce a few centimeters or even a meter or two, it bounced a kilometer. Okay, and then came back somewhere completely different. So you've got to find a solution to that in principle. I mean, you can't do this on an air table. But nevertheless, you're not in reality going to get 5 attempts to latch on. You've got to latch on the first time, or that's it. So I think one of the things you might do is at least think, what am I going to do if we don't latch on the first time? What am I doing in reality? And the answer is you have to use the gas jets, and they have to be reliable. Unlike, by the way, on Rosetta, where they failed, so that's why it mounts so high. But overall, I thought it was a very good job. You've got a good analysis. Again, as in some of the other presentations this morning, you didn't have a full risk analysis, which you need. You were sort of lucky in a way that things went so well, but a lot of the time as engineers, you make your own luck. So well done on that, and well done on a great presentation.
Any questions from Dr. White or Professor Mangum?
Good job, guys.
Go and ask the supervisors.
Any other questions from the audience? Going once, going twice.